Previously, we covered the core foundations. Now in part 4, we tackle Moon, exploration and future missions. The last episode covered the Moon's geology, the craters, lava plains, and internal structure built up over billions of years. Today, we're looking at what humans have actually done there, and what's being planned next. The question running through this episode is straightforward. After more than 60 years of lunar exploration, why are we going back? And what do we genuinely hope to find? It matters right now because, for the first time since Apollo, multiple space agencies and private companies are actively sending hardware to the lunar surface. The decisions made this decade will shape what humanity does in deep space for a very long time. Let's start from the beginning. The race to the moon didn't begin with astronauts. It began with robots, and most of them failed. Between 1958 and 1968, the US and the Soviet Union launched dozens of spacecraft toward the moon. The majority either missed entirely, lost contact, or crashed. Reaching another world turns out to be extraordinarily difficult. Even when it's only 384,000 kilometers away, roughly 100 times Earth's diameter. The Soviet lunar program landed the first spacecraft on the moon in February 1966. Luna 9 touched down in the Ocean of Storms, a broad volcanic plain on the near side, and sent back the first photographs taken from the surface. They showed a rubble-strewn landscape, dusty, uneven, utterly still. Nobody had been certain the surface would actually support a lander's weight. Luna 9 answered that question. The American Surveyor program followed, placing 5 successful landers on the surface between 1966 and 1968. These weren't just taking photographs. They were measuring soil strength, testing surface composition, and preparing the ground, literally, for human boots. Which raises a question I want to park for now. Did those early robotic missions tell us everything we needed before sending people? The answer is more complicated than it sounds, and we'll come back to it. Apollo 11 landed on July 20th, 1969. Neil Armstrong stepped onto the surface at 0256 Universal Time on the 21st. The Sea of Tranquility, where Eagle touched down, is one of those ancient lava plains, flat and relatively clear of large boulders. It was chosen for safety as much as science. Armstrong and Aldrin spent just over 2 hours on the surface, collected 21.5 kilograms of rock and soil, deployed a handful of instruments, planted a flag, and left. 6 more Apollo missions followed. 5 landed successfully. Apollo 13, launched in April 1970, suffered an oxygen tank rupture en route and never landed. The crew made it home, but only just. The 5 successful landings after Apollo 11 were scientifically richer than most people realize. Apollo 15, 16, and 17 each carried a lunar roving vehicle, an electric buggy that let astronauts travel kilometers from the lander rather than just a few hundred meters. Apollo 17 in December 1972 included a trained geologist, Harrison Schmitt. His samples from the Taurus Littrow Valley remain among the most scientifically valuable material ever returned from another world. Then, almost without warning, Apollo stopped. Funding was cut. Political interest moved elsewhere. The last human to walk on the moon was Gene Cernan on December 14th, 1972. Nobody has been back since. That gap, more than 50 years, is one of the most striking facts in the history of space exploration. So what did Apollo actually teach us? Quite a lot, and some of it was genuinely surprising. The moon's surface gravity is about 1/6 of Earth's, roughly 1.62 meters per second squared. Its diameter is 3,474 kilometers, just over a quarter of Earth's. There's no global magnetic field and no significant atmosphere. What it does have is a thin exosphere, a scattering of atoms that don't interact with each other, the way a true atmosphere would. Sodium, potassium, helium, hydrogen. No meaningful protection from solar radiation or micrometeorite impacts. Surface temperatures swing wildly. On the sunlit side, they reach around 127 degrees Celsius. In shadow, they drop to around minus 173 degrees Celsius. Inside permanently shadowed craters near the poles, temperatures can fall to around minus 240 degrees Celsius, making them some of the coldest stable environments in the entire solar system. The Apollo rocks also told us something fundamental about where the moon came from. The samples are chemically very similar to Earth's mantle, but depleted in volatile elements, things like water and carbon compounds that would have boiled off in a high-temperature event. This supported what we now call the giant impact hypothesis. Early in Earth's history, something roughly the size of Mars struck our planet, and the debris from that collision eventually coalesced into the moon. It's the leading explanation, though scientists are still refining the details. Now, back to that open question. Did the robotic precursor missions tell us everything we needed before sending people? Not quite. Apollo was driven by speed and political pressure as much as science. Many of the most important geological sites, the lunar poles, the far side, the ancient highland terrain, were never visited at all. The robotic missions gave us enough confidence to land safely. They didn't give us a complete picture. That picture is still being assembled. Filling in those gaps is exactly what the next generation of missions is trying to do. After Apollo, the moon wasn't entirely abandoned. Exploration just slowed and spread across more countries. In the 1990s, the American Clementine spacecraft mapped the entire lunar surface, and the Lunar Prospector mission detected hydrogen concentrated near the poles. A tentative hint that water ice might exist in permanently shadowed craters. That hint became considerably stronger in 2009, when NASA's El-Cross mission deliberately crashed a rocket stage into the Cabeus crater near the South Pole and analyzed the resulting plume. Water was confirmed. Not a great deal of it. Concentrations perhaps similar to very dry desert soil. But it's there. This matters enormously. Water ice near the lunar poles could be used to support long-duration human presence on the moon. Split it into hydrogen and oxygen, and you have rocket propellant. Keep it as water, and you have a drinking supply and a radiation shield. The moon stops being a dead end and starts being a potential staging point. India's Chandrayaan-1, which arrived in orbit in 2008, also detected water signatures across a surprisingly wide area of the lunar surface, not just at the poles. China's Chang'e program has expanded its ambitions steadily, landing rovers on the near side, and in 2019 becoming the first mission ever to land on the far side. The far side never faces Earth, geologically older in places, and permanently shielded from radio interference, which makes it a strong candidate for future radio astronomy. Chang'e 5, in December 2020, returned the first new lunar samples to Earth in more than 4 decades. Just 1.7 kilograms, from a geologically young volcanic region. Analysis suggested volcanic activity on the moon continued more recently than previous models predicted, possibly as recently as 2 billion years ago, well after scientists thought the moon had gone geologically quiet. That's a significant revision, and a reminder that the moon hasn't finished teaching us things. So, what's being planned? NASA's Artemis program is designed to return humans to the moon. Artemis 1, an uncrewed test of the Space Launch System and Orion capsule, flew in late 2022 on a trajectory that looped around the moon and back. Artemis 2 will carry 4 astronauts on a similar path without landing. Artemis III, currently planned for later this decade, is intended to land crew near the lunar South Pole, the first crewed lunar landing since Apollo 17. The South Pole is the target for a specific reason. That's where the permanently shadowed craters are. That's where the water ice is. If we're going to establish any kind of sustained human presence on the moon, local resources are essential. Bringing everything from Earth, food, water, propellant, is prohibitively expensive over any extended timescale. Alongside Artemis, NASA's Commercial Lunar Payload Services program has been funding private landers to deliver scientific payloads to the surface. Intuitive Machines' IM-1 mission, landing in February 2024 near the South Pole, was the first American soft landing on the moon in over 50 years. It tipped slightly on touchdown. The surface was icier than expected in places, but transmitted data before communications were lost. A small mission, but a significant one. ESA, Japan, and India are all contributing to the broader Artemis framework or pursuing their own programs. India's Chandrayaan-3 landed near the South Pole in August 2023, a landmark achievement, and its Pragyan rover operated for just under 2 weeks before the lunar night halted operations. Among its findings, direct confirmation of sulfur in the surface soil at that latitude, something that hadn't been measured there before. China and Russia are also discussing a joint research station near the South Pole, with timelines extending into the 2030s and beyond. The moon is, right now, busier than it's been at any point since the 1970s, and the ambitions are considerably larger. There's a practical argument and a scientific one for all of this, and they're worth separating. The scientific case is clear. We've sampled 6 locations on a body 3,474 kilometers in diameter. Humans haven't touched the far side. The poles remain unvisited by any crewed mission. We don't fully understand how the interior evolved, how the crust varies across hemispheres, or exactly how much water sits in the shadowed regions, or in what form. The moon is a record of the early solar system. Its rocks predate anything preserved on Earth. Reading that record more completely would tell us a great deal about how our planet and life on it came to exist. The practical argument is about proximity. The moon is 3 days from Earth by spacecraft. Mars is 6 to 9 months, depending on orbital alignment. If we want to build the knowledge, techniques, and hardware needed to keep humans alive and productive in deep space, the moon is the right place to start. Not because it's easy, it isn't, but because if something goes wrong, you can get people home in days rather than months. There are also open questions about long-term human health in low gravity. We know a great deal about the effects of microgravity from the International Space Station. What we don't know is what living at 1/6 gravity does to the human body over months or years. The moon is the only nearby place where we can actually find out. Here's the thing worth sitting with. We've been to the moon. We know it's possible. What we're now trying to understand is whether it's sustainable, whether humans can live and work there in a way that's useful, repeatable, and not entirely dependent on constant resupply from Earth. That's a harder problem than getting there. It's the problem the next decade of exploration is genuinely trying to solve. The missions being launched right now aren't about flags and footprints. They're about whether the moon becomes somewhere humanity actually uses, or whether it remains a destination we visited once and then watched from a distance. That shift in thinking, from destination to outpost, is what makes this moment different from the 1960s. Next episode, Part 5 takes on one of the most fundamental questions the moon raises. What does its existence tell us about how Earth formed, and whether planetary systems like ours might? That is Part 4 of Moon. Subscribe so you do not miss it.